Let me show you around the PL0 recursive descent parser that you're going to be having a look at in tutorial 4. The parser is a recursive descent parser. You can find it in parser.java, which is in the parse package. Before we have a bit of a closer look at that, let's have a look at how we can take a PL0 program and we can execute it using the tutorial 4 compiler. In the test program folder, you'll find a number of different PL0 programs. If you open up one of those, you can run it by selecting Run PL0 and choosing to run it. That will run it with the tutorial 4 compiler. What it's doing is it's running pl0.pl0rd, where rd stands for recursive descent. So it's running this compiler on the file that you currently have open in your current working directory. So because I've currently got a PL0 file open, it's going to run the compiler on that file. What the compiler does is it parses the program, it then performs some static semantics analysis on it, and then it actually runs it using an interpreter. We'll focus on the parsing phase for now. Because this program doesn't have any syntactical errors, none are reported here, the parsing phase just completes successfully. If we introduce some errors, then it will recover as best it can using the syntax error recovery strategy that we described during the lectures. So if I replace this assignment equals symbol by just an equals and I run it, then hopefully the parser will tell me about that. It will say, right, there's a problem here. When I was parsing an assignment, I expected an assignment symbol, but instead I was just given this equals symbol here. In this particular case, it's able to recover quite well from this small problem. And so if there are other problems occurring down here, it's going to be able to give me some meaningful feedback about them as well. So if I introduce another then statement here, then after it discovers this error in the assignment statement, it's able to recover and go on and tell me something meaningful about the error that's occurred down here as well. Remember though that our error recovery isn't perfect, and in some cases errors might cascade and get away from us, and they're going to be sort of hard to understand what's going on from the output, in which case as a programmer you're just going to have to go back and fix the simple errors so that you can get more meaningful feedback about the errors that are occurring later on. Okay. Let's fix up those problems. Right. One thing you might want to do is you might want to run the compiler in debug mode. So we can go and do that if you like. Let's edit the configuration of run PL0 so that it runs the compiler with the debug option turned on. If we do that, what's going to happen is our output is all of a sudden going to become a lot more verbose. So as it's parsing the program, it's going to tell us exactly what it's doing. So it starts out trying to parse the non-terminal symbol program. It even reports to us what the error recovery sets are for each of the non-terminals that we're visiting. So when it parses a program, this is its error recovery set. So after it starts parsing a program, it starts parsing a block and then a declaration and then a variable declaration list, etc., all the while telling us what its error recovery sets are. If we come down here a bit further, we can see where it starts parsing the actual statements in the body of this main method. So down here it starts parsing a compound statement and then a statement list and then a statement. The assignment statement gets started. It tells us when it's finished with that later on, etc. One slightly annoying problem is that if we turn the debugger on, if we have any error, syntax error information, it's going to get lost in all this debugging mode, debugging information here. So here's my syntax error recovery message, and it's sort of lost in all this debugging stuff. So if you want to see exactly what your syntax errors are, you might want to turn the debugging mode off again and run it again so that you can see that a bit more clearly. Oops. Right. Let's go now and have a look at the parser itself. Let's focus on how it's performing the parsing for expressions and for statements. When we parse an expression, we need to return the abstract syntax tree associated with that expression. That means that we're going to have to return an expression node. So the first thing we're doing in the code here is we're setting up a parse method for expressions that is set to return an expression node. And it's also set up so that if it encounters an error, it's going to return an error node, an expression node error node. So if it's trying to parse a non-terminal symbol that's meant to be an expression and it can't quite do it, it encounters a problem during its synchronization phase, its start synchronization phase, it will return one of these error nodes. So this here is setting that up. The next thing we do in the code we have here for parsing expressions is set up some of the start sets for our non-terminal symbols. So here we're setting up the set of tokens that we're expecting an L value to start with. So that's easy. So an L value just starts with an identifier. We set up that set here. We set up the set of tokens we're expecting a factor to start with. That's the L value start set, union together with a number and a left parentheses. And here are the tokens that we're expecting a term to start with, and they're just a factor start set in this case, an expression to start with, etc. All right, so we set up a number of constant declarations that we're going to use throughout our parse methods. Okay, and now we come down and we start actually parsing these expressions. The first method we have here is for parsing a condition. But the rule for a condition is just ridiculously simple. We just parse a rel condition in this case. So we sort of, maybe that one's not very interesting. Let's have a look at parse. Let's have a look at parse rel condition instead. When we parse a rel condition, we're getting the method expression.parse to do our error recovery for us, our synchronization at the start and the end of the method. We have to tell it what the name of this non-terminal is, so rel condition, and it can use that for debugging information and for error reporting. We then need to tell it the set of tokens, the set of symbols that we're expecting a relational condition to start with. We've already defined them up above. We tell it what its recovery set is, and then we need to also pass it a method that is actually going to parse the relational condition in the case that the synchronization at the start of the method was successful and it was able to find a token which is in the relational condition start set. Okay, so this code is going to start looking familiar because we've been through similar code during the lectures. What we're going to do is we start out by parsing an expression, right? And we set our abstract syntax tree that we're going to return to begin with just to be the value that was returned by parsing that expression. When we parse an expression, we've got to tell it the set of symbols it has to use to recover on. The set of symbols it's going to use to recover on are going to be the set of symbols that a rel condition recovers on, together with the things that can immediately follow it here, which is going to be the relop set. So a relop can come after this expression, so we'll recover on anything a rel condition can recover on, and we'll also recover on anything that starts one of these relops. Then we've got optionally another relop followed by an expression. How do we implement optional statements? Well, we do that using a conditional. We check to see if the token we're currently looking at is something that could start a relop. If it is, we parse a relop and an expression. If it's not, we just end, and in this case we're going to replace the we're going to return the abstract syntax tree corresponding to the condition we read in to begin with. But right, what happens if we are going to read in this optional part? So if the token we're looking at is in relop set, then what we do is we get the location of the relop, and then we get the operator that it corresponds. We get the operator that it corresponds to by parsing the relop. So when we parse a relop, it's going to return an operator in this case. We can go and we can have a look at what the operators are. They're defined here in the package tree. The package tree keeps all our abstract syntax tree classes together. So if we go and have a look in tree, that's where we're going to find our expression nodes being defined, and it's where we're going to find our statement nodes being defined, and also these operators that we're having a look at here. Oops. Okay, so parsing relop returns me an operator. When I parse my relop, it also needs a recover set. So what's it going to need to recover on? Anything that the rel condition can recover on, plus any token that can immediately follow it in this grammar rule here. So anything that can start an expression, right? So we've read in our operator, the location of the operator, and then we read in, and then we parse our expression, and we record what its abstract syntax tree was, so what it returned. That parse expression needs a recover set, which is going to be the recover set of the relational condition itself. And then in this case, what we need to do is we need to build up a new expression node, which is a binary node that has the location of the operator code, so what operation we're performing, and then it needs two arguments, an abstract syntax tree that represents the left-hand side and then the right-hand side of what this binary operation is being applied to. Okay, and at the end we just return our condition, we return our abstract syntax tree for this particular expression. We should probably go in and have a look at exactly what this expression node class is that's defined in the tree package. So expression node is just an abstract class that has a location and a type. Inside expression node, we have a bunch of subclasses defined that aren't abstract. So if I come back here, I can see that binary node is a subclass of expression node, and a binary node, as well as having a location and a type, it also has an operator and it has a left and a right argument. Right? So here's our binary node being defined for our abstract syntax tree. Okay, so that's us parsing a relational condition. Maybe we should have a bit of a closer look at this parse relop. So when we parse our relational operator, it returns our operator. It also needs to do error recovery, so it's got an error recovery set. Here we're not using the parse method for expressions, we're using a parse method for operators. So the difference here is that a parse method for operators returns an operator, and if it's not able to do its synchronization properly at the start of a method, it's going to return an operator.invalidOp. So it's going to return an operator that represents an invalid operator if we can't read this properly, instead of returning an expression node error node. Right, so we've set it up to work properly there. Right, when we're parsing our relational operator, we're expecting one of these things: an equals, a not equals, a less, a greater, or a less than or equals, or a greater than or equals to symbol. And so when we've got a number of different alternatives here in our recursive descent parser, we can implement that using a conditional statement that checks which one we've got. Instead here I've used a switch statement. So what we've done here is equivalent to having an if statement. So we've just switched on the kind of the current token. So you might not have seen us use this method before. Tokens.getKind is going to tell us if this is an equals, an n equals, a less, a greater than, an l equals, etc. If it were an identifier node, it would tell us it was an identifier node, right? So it breaks things up into the different cases. If it's an equals, it gets the operator code operator.equals, and then it matches the equals symbol. And this operator code is going to be what it returns at the bottom, and it handles these other cases in a similar way. If it can't match any of these alternatives, then what it's going to do is it's going to report a fatal error. It's going to report a fatal error in that case because because this parse method takes care of synchronization at the start of the method. Synchronization at the start of the method guarantees that our current token, after we've synchronized, is going to be in rel offset. So it is going to be one of these alternatives. So if it wasn't one of those alternatives, we'd have a really big problem. We're going to use some defensive programming and just report that there. Right. So we've had a look at parse relup, we've had a look at expression nodes. Let's go down and have a look then at how we parse statements. Here we go. So when we parse statements, our methods are going to have to return an abstract syntax tree corresponding to a statement node. So here we set up our parse method for statement so that it returns statement nodes instead of expression nodes or operators or something like this. And if we're parsing a statement and we have an error in our synchronization, what we're going to do is we're going to return a statement node error node with the current location of the error. So we set up our parse method to begin with. We then set up the set of tokens that a statement can start with so that we can use that in the code that follows. Okay. Let's go down and have a look at the implementation of, let's say, a conditional statement. Here we go. So let's parse an if statement. Let's see how we do that in the compiler. So to parse this conditional statement, what we do is we use statement.parse to do our error recovery at the start and the end of the parse method. We need to give it a string telling it what this non-terminal symbol is that it can use for error reporting. We then need to tell it what tokens we're expecting a conditional statement to start with. That's just a single token in this case. It's going to be the keyword if. We need to give it our recover set that it's going to recover on if it needs to. And then we need to give it a method that actually parses the conditional statement if it's able to do the synchronization properly at the beginning. So what happens in this? What happens to actually parse a conditional statement? Well, the first thing we need to do is match this keyword if. We know when we start this code that the current token is going to be keyword if, so we don't need to do any error recovery for this first match. We then get the location of the current token, which is going to represent the condition. So the location of this conditional statement is going to be treated as the location of the condition. And we're just doing that because usually if there's an error in a conditional statement, it usually occurs in the condition itself. So we'll set the location of the if node that we're creating to be the location of this condition statement. So we'll get the location of that condition and then we'll parse the condition, and when we do, it will return to us an expression node. So we'll keep track of that. We'll tell it to recover on the recover set of this method unioned together with what can come immediately after it, which is the keyword then. Right. And then we'll match the keyword then, but when we do it, we have to take into account error recovery. So we'll tell it what to recover on. We'll tell it to recover on the statement start set. So remember that our terminal symbols, we do local error recovery. So in this case, we're going to recover on tokens that can follow immediately after. That will be the statement start set in this particular case. We then parse the statement, the then part of the statement, and that's going to return a statement node. When we parse it, we have to tell it what to recover on. We'll tell it to recover on our recover set, so the recover set for the conditional statement, together with the thing that can immediately follow it, which is a keyword else in this case. Then we'll match the keyword else. But when we match it, we'll tell it to do local error recovery using the set of the set of tokens that can occur immediately after it, which is the statement start set in this case. Then what we'll do is we'll parse the statement, we'll parse this statement here, and we'll record the abstract syntax tree that it returns, which is going to be a statement node. Its recover set in this case is just going to be the recover set of the conditional statement as a whole, because nothing comes after it here. So at the end, what we're going to do is we need to actually build up our abstract syntax tree result. It's going to be a statement node, which is an if node. And that if node is going to have a location, which was equal to the location of the condition we read in, which is going to be an expression node, a then clause, which is going to be a statement node, and an else clause, which is also going to be a statement node. So what's this statement node? Well, look, it's also defined in this tree package. And what it is, well, a statement node has a location. It's an abstract class that has a location. And inside of it, we have a number of subclasses defined. So the subclass that we're interested in is this if node class. And if node, as well as having its location, it also has an expression node corresponding to its condition, a statement node corresponding to its then statement, and a statement node corresponding to its else statement, and a bunch of getter and setter methods and stuff there. Okay. One of the interesting things to notice is that some of our error recovery is a bit redundant. If we have a look at how to parse a statement, we'll see that we're only going to parse, say, a right statement if we know that the current token is a keyword right. But if we go down to parse right statement, we'll see that statement.parse performs synchronization at the start of the method and the end of the method. The synchronization at the start of the method isn't necessary in this case because we know that the current token is a keyword right. So we know that we don't need to skip tokens until we get to one that's either a keyword right or in recover set, because we don't have to do it. But we put in sort of all of this error checking anyway, just partly for consistency and just also to make sure that we haven't made any mistakes in our code. It helps us pick up on when we make errors. Right, so that's a bit of an overview of how the recursive descent parser for the tutorial 4 compiler works. So it just implements the recursive descent parser using all the techniques that we've described during lectures.